What is the three-body problem? The universe is a dance of celestial bodies, each exerting a gravitational pull on the others. Understanding these interactions is at the heart of astrophysics. The two-body problem is simple, but add a third object, and the n-body problem emerges. A complex puzzle. Isaac Newton's law of universal gravitation elegantly describes the force of attraction between any two objects with mass. It provides the foundation for understanding how planets orbit stars and how moons orbit planets. However, when applied to three or more bodies, Newton's elegant equations become incredibly difficult to solve. The reason lies in the interconnected nature of the gravitational forces. In a two-body system, we can consider one body as stationary and calculate the other's orbit. However, with three or more bodies, each object's motion is influenced by the constantly changing positions and velocities of all the others. This creates a tangled web of interdependence that makes it impossible to derive a single equation that can predict the precise motion of each object into the distant future. The n-body problem introduces us to the fascinating interplay of chaos and determinism in celestial mechanics. A system is considered chaotic if even tiny differences in initial conditions can lead to vastly different outcomes over time. Think of the classic butterfly effect, where a butterfly flapping its wings in Brazil could, in theory, set off a chain of events that results in a tornado in Texas. While it might seem counterintuitive, chaotic systems like those governed by the n-body problem are also deterministic. This means that if we knew the exact positions, velocities, and masses of all objects in the system at a given moment, we could in principle predict their future movements with perfect accuracy. However, this determinism is often masked by the extreme sensitivity to initial conditions. Section 4. The Butterfly Effect in Space, a Solar System Simulation. To illustrate the sensitivity of n-body systems, let's imagine a thought experiment where we run a sophisticated computer simulation of our solar system over billions of years. In the first simulation, we let the system evolve as it is. In the second simulation, we make a minuscule change. We shift Mercury's initial position by just 1 millimeter closer to the Sun. While this change seems insignificant, the long-term consequences are anything but. Over billions of years, this tiny alteration in Mercury's initial position can cascade through the system, amplifying with each planetary interaction. In some simulations, this could lead to Mercury being ejected from the solar system altogether. In others, it might trigger a collision between planets, a cosmic billiards game with unimaginable consequences. This thought experiment highlights the profound challenge of long-term predictions in celestial mechanics. Even with our most powerful computers, the slightest inaccuracies in our knowledge of initial conditions can render predictions of the distant future unreliable. Section 5. Navigating the Cosmos, Applications and Approximations. The n-body problem isn't just abstract, it has real-world implications in space exploration. Understanding celestial mechanics is crucial for planning missions and predicting trajectories. Simplified models like the restricted three-body problem make predictions more manageable. This challenge drives innovation and deepens our cosmic understanding. Don't forget to like, share, and subscribe for more fascinating insights into the universe.